Well, howdy there, Internet students. Look at here. We are up to chapter 11. Uh, you know how at the beginning of the chapter there's this get ready part? I think you should go over these and make sure you know how to do it. So pause now and then you can check back and see if you got the right answers. All right, here's your answers. Remember, these are important skills for being successful in this chapter. Some quick vocabulary details to take care of. We're going to be talking about different parts of polyhedra. So go ahead and do this vocab review. And you can see if you got the right answers here. So we're going to be talking about three-dimensional shapes. We're going to specifically polyhedra in this 11.1. So cross out the figure below that is not a polyhedron. That would be this one. Okay. So go ahead and figure out what X is, what Y is, and what Z is for this rectangular prism. And we're going to try and see if there's a relationship between the three. So this dude named Leonhard Euler, and his last name is spelled like that, noticed that there's always a relationship with polyhedra between the number of corners, which we're going to call vertices, the number of flat surfaces, which we're going to call faces, and the number of folded creases, which we're going to call edges. He noticed that the number of vertices and faces together is always two more than the number of edges, which is kind of cool. So with more difficult polyhedra, we can use that formula to help us figure out how many of each of these parts there are. Okay, so first let's talk about what are the vertices, what are the edges, and what are the faces in polyhedra, and we're going to list them below. First, why don't you just give it a shot, see if you can figure out how many edges there are, how many faces there are in this polyhedra, and how many vertices there are. And then check to see if what we just talked about with Euler's formula is true. So you should have got numbers like this, and once again, the number of edges is 2 less than the total number of faces and vertices. Now, just so we get this clear, we're gonna consider edges are line segments, like RT is one of the edges, one of the 6 edges, segment RT. The faces are going to be two-dimensional shapes. In this case, they're all triangles. So we're going to say one example of a face would be triangle STU. And then the vertices are points. So we're just going to use a capital letter to represent those. So the vertices are R, S, T, and U. All right, why don't you do the next problem? See if you can figure out how many vertices, edges, and faces there are and list them. All right, so here they are. You should have got 6 vertices, 9 edges, and 5 faces. All right, so here's the concept. The number of faces plus the number of vertices is equal to the number of edges plus 2. You can verify that on the last couple problems we did, but it is true. So we're going to use that and figure out how many edges by using the formula. So let's count just the vertices plus the faces. And we know that the number of edges will be 2 less than that total. So the number of faces is 1, 2, 3, 4, 5, 6, 7, 8. The number of vertices, those are the corners, there's 4 here, then 1 on each end, so that's 6. That should equal the number of edges plus 2. Well, since 8 plus 6 is 14, then that means the number of edges must be 12. All right, you try one, see if you get it right. You should have got 12 for the number of faces there according to the formula. Now, Euler's formula also works in 2 dimensions, so if you draw a net of an object, you can use this formula. The only difference is that the number of faces plus the number of vertices is equal to the number of edges plus 1. Take note of that. Let's show that on the net of a cube. So let's do a real simple net of a cube here. We need 6 faces, right? So there's 6 faces. Let's go ahead and count those out. And the number of vertices, those are the corners. Let me change colors of pen here so we can see those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of those. Okay, so we have, and now we just have to count the edges, and those are the line segments in between. Let's change colors for those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And you can see that the count works out for that. All right, go ahead and verify Euler's formula here by counting up the number of faces, the number of vertices, and the number of edges, and showing that the formula works. All right, now the last thing we're going to talk about is what the cross sections look like in 3-dimensional polyhedra. And there's some sort of a shape. In this case, if we do a vertical cut of this triangular prism the way it's set, and we get a triangle. Imagine if we did a horizontal cut that would look like this. Trying to do a dotted line there. That shape would be a rectangle. So depending on how you cut it, you can get different 2-dimensional shapes. So that the cross section is a plane figure. All right, so if we cut this cone horizontally, nice spelling there. So we cut it right here, what you would get is a circle. If we cut this vertically, so let's say we cut it like this, that shape would be a triangle if we cut it vertically. All right, so go ahead and think about this solid here. What cross section would you get when you cut it vertically? Oh, horizontally, sorry. Should have got a circle. Okay, now we're going to try and learn how to draw these cross sections and then decide what they are. In this case, we want to do a vertical plane cut. So if we cut it vertically, these 2 sides would be solid. Those are sides you see. And then the back lines would be dotted. You don't see those in the bottom also. But we could see that the shape would be a rectangle. All right, good luck with the work. We'll talk to you soon.